Slide 1 Introduction. Greetings, students, and welcome to today's exploration of an intriguing algorithmic challenge. We will delve into LeetCode Problem 21, aptly titled Merge Two Sorted Lists. This problem invites us to unite two pre-sorted linked lists into a single cohesive sorted linked list. Imagine we have two lists, List 1 containing the elements 1, 2, 4, and List 2 with 1, 3, 4. Your task is to merge these lists while preserving their inherent order. The expected outcome here is a new list showcasing the combined elements in sorted fashion. 1, 1, 2, 3, 4, 4. This exercise not only sharpens your skills in linked list manipulation, but also enhances your understanding of sorting algorithms. So, let us embark on this intellectual journey together and unravel the intricacies of merging linked lists. A linked list is a fundamental data structure composed of nodes. Each node has two main parts: the data it holds, and a reference to the next node in the sequence. Think of it like a chain of paper clips, where each clip holds a piece of information and points to the next clip. This structure allows for efficient memory usage because linked lists do not need contiguous blocks of memory, unlike arrays. There are different types of linked lists. Singly linked lists only point to the next node, while doubly linked lists also point back to the previous node, making them easier to navigate in both directions. The flexibility of linked lists shines in situations where the size of data isn't fixed, such as managing stacks and queues. When we manipulate linked lists, we perform operations like insertion and deletion. For example, adding a node involves adjusting the pointers around it, while deleting a node requires bypassing it. These operations can be very efficient, taking constant time when done at the start of the list. This efficiency makes linked lists a powerful tool for dynamic data management. In this slide, we have a basic implementation of a linked list in Python, focusing on merging two sorted lists. We begin with the node class, which represents each element of our linked list. Each node contains data and a pointer to the next node, which helps us traverse the list. Next, we see the linked list class, which manages the nodes. It starts with an empty list, where the head is set to none. The append method allows us to add new nodes to the end of the list. If the list is empty, the new node becomes the head. Otherwise, we traverse the list until we reach the last node and link the new node. Finally, the display method is used to print all the elements in the list sequentially. We create a linked list, append 3 numbers, and display them in order. This structure is fundamental for understanding how to manipulate lists effectively, especially when dealing with sorted data. The two pointers technique is an effective strategy for tackling problems that involve sequences. In this example, we're using the two pointers technique to merge two sorted lists. First, we initialize two pointers. The left pointer starts at the beginning of the array, while the right pointer is set at the end. This setup allows us to explore the array from both ends simultaneously. Next, we enter a loop that continues until the left pointer meets the right pointer. Inside the loop, we sum the values at both pointers and add that sum to our result list. After each addition, we move the left pointer to the right and the right pointer to the left. This movement ensures we are gradually converging towards the center of the array. Finally, when the loop ends, we return the result list, which now contains the sums of pairs from both ends of the array. This method is efficient and highlights how two pointers can simplify problems by reducing the need for nested loops, making our solution more elegant and faster. The function shown here, double elements, is a great example of iterative traversal. It starts by creating an empty list called doubled list, which will hold our results. Next, it enters a loop that goes through each item in the input list. Think of this as a teacher going through each student in a class, checking their homework one by one. For every element found, the function doubles its value. Just like if we had a basket of apples and we wanted to put 2 apples in the basket for every one we picked. Finally, it adds this doubled value to doubled list. After finishing the loop, the function returns the complete list of doubled elements. This process illustrates how we can systematically handle each item in a collection, which is fundamental in programming. By understanding this, you're laying the groundwork for working with more complex data structures and algorithms. LeetCode problem 21 involves merging 2 sorted linked lists. Here's a straightforward algorithm to tackle this. First, we need to define the list node structure, which has a value and a pointer to the next node. This is essential for understanding how our linked lists work. Next, we create a dummy node. This dummy serves as a placeholder at the start of our merged list, making it easier to return the final result later. We also initialize a pointer called current, which will track the end of our merged list. Then, we set up 2 pointers, L1 and L2, pointing to the heads of the respective input lists. Now, we enter a loop that runs as long as both lists have nodes. We compare the values at L1 and L2. The smaller value gets added to our merged list, and we move the pointer of that list to the next node. After the loop, there may be remaining nodes in one of the lists. We simply connect the end of our merged list to whichever list still has nodes left. Finally, we return dummy.next, which points to the head of our merged list. The time complexity of this approach is O(n plus m), where n and m are the lengths of the lists, and the space complexity is O1, as we only use a few extra pointers. Here's a quick look at the implementation in Python. This concise approach ensures that we maintain the sorted order while merging the 2 lists efficiently. Today, we explore LeetCode problem 21, which asks us to merge 2 sorted linked lists into a single sorted linked list. The merging process must respect the order of the nodes, achieved by splicing nodes from the input lists. Notably, the input lists are guaranteed to be sorted in non-decreasing order, with each containing between 0 and 50 nodes. Additionally, each node's value falls within the range of -100 to 100, shaping our approach to the solution. The provided Python code tackles the problem of merging 2 sorted linked lists into 1 sorted linked list. This is a common task when working with data structures. At the core of this solution is the listNode class, which represents each node in the linked list. Each node holds a value, referred to as val, and a reference to the next node, named next. The constructor of this class initializes these 2 attributes, allowing us to create linked list nodes dynamically. Next, we have the merge2lists function, which uses an iterative approach to merge the 2 lists. To simplify the process, especially in cases where one list might be empty, we start with a dummy node. This dummy node acts as a placeholder, making it easy to return the head of the merged list later. Inside the while loop, the algorithm compares the values of the current nodes from both lists, L1 and L2. If the value from L1 is smaller, that node gets added to the merged list. We keep a pointer called current, which points to the last node of the merged list, updating it after each addition. Once one of the lists is exhausted, we simply append the remaining nodes from the other list. This algorithm runs with a time complexity of O(n plus m), where n and m are the lengths of the input lists. The choice of an iterative approach helps prevent stack overflow issues and optimizes space complexity to O1, aside from the input space needed for the lists. These design choices reflect a strong understanding of linked list operations and effective merging strategies, resulting in an efficient solution. The time complexity for merging 2 sorted lists is O(n plus m). Here, n represents the length of the first list and m represents the length of the second list. This means that the time it takes to merge the lists grows linearly with the total number of elements. We traverse each list only once, comparing elements and merging them into a single sorted list. Now let's talk about space complexity. It is O1, which means we're using a constant amount of space regardless of the input sizes. We achieve this by merging the lists in place without creating new data structures. Essentially, we only need a few pointers, one to track the current position in the merged list, and others for the current nodes of each list. This efficient approach keeps our algorithm both speedy and memory-friendly, making it a great choice for merging sorted lists.